I'm going to talk to you about WebAssembly and do a deep dive about what actually WebAssembly is. So my name is Sohan. So I thought I'll do something different for this talk. Right? So I'm going to try and explain to you what WebAssembly is, but I've also sort of woven the history of Bangalore as a city into this talk. Right? I'm someone who's interested in like the history and culture of the world, and having lived in Bangalore for so many years, it's something that has always interested me. So if you're interested in either the history of Bangalore or WebAssembly, or ideally both, this talk might be of interest to you. So has anyone here used or played around with WebAssembly? Anybody? Few of y'all? Awesome. Okay. I'm sure most of y'all have at least heard of it in the news. It's been getting a lot of press, I think, in the last year and a half or so, right? And it's gaining a lot of popularity. In fact, I was at KubeCon in Paris about a month ago, and WebAssembly actually was one of the most spoken about technologies at KubeCon. Right, so this is an analysis of all the tweets at KubeCon from this year from an analyst, and WebAssembly or WASM was actually #1, which is pretty cool. And the reasons why this is happening is what I'm here to talk to you about. Now, WebAssembly as a technology has been there since the mid-2010s, and it was originally meant for the web. So even right now, companies such as these, like Figma and Adobe and Roblox, they are using it in their front ends for various purposes in production. We're also seeing it being used on the server side of things in companies such as Zeiss, Fermion, of course, where I work. So this is something that you'll probably see a lot more of in the coming months. So let's dive straight in. The textbook definition of WebAssembly, there's a lot to unpack here, right? So the one thing you need to know is it's an instruction format. Right? So it's not a programming language. It's not a proprietary piece of technology owned by a company. It is a binary instruction format, like the other instruction formats that we have right now. And essentially, it is meant for a stack-based virtual machine. It was designed ground up to be a portable compilation target for different programming languages to enable development both on the client and the server side. Lots to unpack here, and I'll get to it very quickly. Essentially, you can write code in any language, convert it into this binary instruction format that could run on the web. It could run on the server side as well, and that was the idea. So it was built ground up for that. A couple of things that also are relevant and that you need to know is, like I said, it started as tech for the browser, right? So the idea was, hey, we need a way for us to be able to run, say, a Python code or a Rust code in the browser. How do we do that? So a bunch of companies such as Mozilla that work on browser tech actually came up with this technology. And it was pretty cool. Companies like Roblox and Adobe and Figma still use it on their front ends. And then slowly, there were advancements made which have enabled it for you to be able to use it on the server side. Right? And that's what I'll speak to you about today. And the words WebAssembly and WASM are interchangeable. It's just a short form. So if I say WASM, I'm talking about WebAssembly. So we're going to dive straight into what WebAssembly is, right? And like I said, it is an instruction format. Now, at the core of any WebAssembly program is what's called a WebAssembly module, right? So this module can be represented in two ways. The first way is, there we go, is a .wasm format. So this is what the binary instruction actually looks like. I don't know about you, but I can't really read any of this or understand what this is. But this is what is sent over networks because it is easier to send and it is much faster to parse. Right? So when you're writing, say, a WebAssembly code on the server side, this is probably what's being sent because, well, it's more efficient. If you're into like the compiler debugging side of things, there's also a text version of WASM, which is a .wat, right? So you see a simple function to add two numbers in your .wat file, and that is the binary representation, or .wasm, which you will see out in the wild. Yeah. So these are the two representations. The text format that you see below uses something called S expressions, which is basically like a hierarchical way to sort of represent something that's flat. Yeah. So this is a simple program to add two numbers. And you're essentially doing the same thing in a sort of decision tree, which is called an S expression. We're not going to go into the depths of this because it's not super relevant, but you can see the function says add there's one parameter, there's a second parameter, both 32-bit integers. You get the two parameters, and then you add them, and that's essentially what you see. You have the WebAssembly module, the function, the parameters, adding, and so on. A basic WebAssembly module, and the simplest WebAssembly module, looks like this. This is the entire program, right? Open bracket, module, close bracket. That's it. Right? Imagine having an error writing this program. I probably will end up doing that. But this is your most basic WebAssembly module, but honestly, it does nothing, right? Absolutely, it's just a module. You can do something more complex like a calculation, right? Again, this is the same program that I spoke to you about just now. You're adding two numbers, two 32-bit integers. You retrieve those numbers, and you write another function to increment a number, right? So it says +1, and you reference that other addition function from this, right? So this is how a typical WebAssembly module would look like. Now, how a WebAssembly module executes, and for a visual representation of this, is something like this, right? You have a function add, have a function called +1, and they sort of reference each other. But hey, wait a minute, there are like random terms on the screen here which says guest WASM module and host runtime. What are these things? I've just sort of introduced them. So, like I said, there's a WASM module. That's the core of any WebAssembly program. The terminology is of calling it a guest and a host, right? A guest is the WASM module, and that WASM module can run on something called a host runtime. For any WebAssembly program to run anywhere, you have to have a runtime, very similar to the idea of a JVM, right? And I'll show you that comparison later, a Java virtual machine. The cool thing with this is this guest WASM module runs on this host runtime, right? And the analogy I would like to draw is like a hotel. So think of the hotel as this host runtime, right? And a hotel has rooms, it has a swimming pool, it has a kitchen. As a guest, you have access only to your room. You don't have access to the other guest rooms, of course, but you might have access to shared things like, say, the hotel or the swimming pool, but you won't have access to, I don't know, like, say, the back office, right? So think of this as a hotel room in a hotel, and the host runtime as the hotel, and that's the analogy. Now, there are four things that make WebAssembly a very attractive proposition to run both in the browser and on server side, right? And they are these four things. The fact that you can write polyglot programming. You can write code in any language which converts to WebAssembly and run that WebAssembly app anywhere. Two is the security sandbox. If you go back to this example here, this guest WASM module runs in this host runtime, has access to nothing in that host runtime. No access to files, no access to outbound HTTP, nothing, right? By default, the access level is to deny all. Now, this is very different from everything from a JVM to a container where the default is allow all, and you have to draw, boundaries to stop access, right? So by default, each guest or each WASM module is security sandboxed. So security is one reason. WASM is a very attractive proposition, especially on the server side. The fact that you can run that WASM module anywhere, right, across architecture, so ARM, Intel, AMD, whatever, across OSs, so Mac, Windows, Linux. You can run it in the cloud, you can run it on Raspberry Pi, it doesn't matter. Any place that has a WebAssembly runtime, you can run that WASM module. So really, it's taking this idea that Java had of write once, run anywhere, and it's like really pushing it to the limit. And lastly is, of course, the performance itself, which is the near-native execution speed. I think we all strive to be as near-native as possible when it comes to execution speed, and WebAssembly provides that. So I'm going to do a deep dive on each of these, how it works under the hood, but I thought I'll do something interesting. So I thought I'd try and tell stories of Bangalore's history, which are analogous to this. Right? So let's actually talk about the fact about polyglot. Right? So I'm going to tell you a very interesting story from way back in history, which is 750 CE, so way back. But the story actually starts in 2017, and this is completely true. So there was this man walking near Hebbal flyover. Any Bangaloreans here who or at least live in Bangalore? Anyone? Few of y'all? Okay. So Hebbal flyover, not too far from here. He was walking on the road, and there was some digging construction going on, as it always happens in Bangalore. And he noticed that there was a stone on the ground, which seemed to have some sort of inscriptions. Right? He was part of like a history society, knew something about history. So he stopped to get a look, and it actually looked pretty interesting. It looked old. It had some inscriptions. So he called some friends over, and he also had some connections, so he got them to stop the constructions. And they dug up all the stones, they cleaned it, they called some historians, and they actually found something very, very surprising. They found this stone that you see here. Now, this stone is very interesting because it has inscriptions in Kannada 100 years before what was thought was the first ever Kannada piece of literature, right? So it predated the oldest Kannada book by about 100 years. And it blew everyone's mind. And the story that was told on the stone was the story of a man now named Hebbal Kittaya. Hebbal is the location, Kittaya was his name. And he basically has, he came with his horse and his entire army towards Hebbal and set up a small kingdom there. And he's considered now as the first resident of Bangalore because he documented everything around him, and he christened that area as well as Hebbal, right? Way before anyone thought that anyone lived in this piece of land. The cool thing is, a bunch of people did crowdfunding to set up this mantapa with that stone. I was involved in the crowdfunding as well. And they unearthed a bunch of other stones dating from 750 CE all the way up to the 15th century. And this is all over Bangalore and the outskirts of Bangalore. And the amazing thing is, this was found in many different languages, not just Kannada. It was found in Halmidi, which is an older version of Kannada. It was found in Tamil, Telugu. So even in the olden days, Bangalore was this hub for people who spoke different languages. And even now, it is a district with the most spoken languages in India, right? So just like Bangalore always has this place, always has been this place where people spoke multiple languages and you had polyglots, WebAssembly too supports polyglots, or the ability to write in different languages. So currently, you have 40 plus languages supported in WebAssembly with various levels of support. So there are different ways to categorize programming languages, and one way is to look at it this way, right? You have systems programming languages like C, Rust, C++, Zig, very low level. So you write code which generates some machine executable, commands, and the computer sort of reads that. The level above that or below that, whichever way you look at it, is a scripting language like Ruby, Python, JavaScript, where there is an interpreter. So there's an intermediate step involved. So you write code, there's an interpreter, the interpreter does a bunch of things to generate machine-readable code, and that's what happens. And the last are the virtual machine or the bytecode languages like Java, Kotlin, and all of the .NET languages, where there is like a virtual machine that reads the output of what you have created, and that virtual machine runs in different places. WebAssembly is fairly new, so the levels of support for these different languages are in a state of evolution. Let's take a look at the first two at least, right? So with the systems programming languages, it's actually very, very well supported, right? One, because they are much more low level, and also the people who supported WebAssembly in the beginning chose these languages to sort of, go in the ecosystem. So Rust, for instance, you can compile that straight to a WebAssembly module, and that WebAssembly module can execute on any WebAssembly runtime, which, like I said, can execute on any architecture and platform, right? It's almost as much as changing a flag in the Rust compiler, right? Which instead of, having a target as an x86, you have a target as a WebAssembly module, and you're done, right? Super easy. Rust is probably the best supported language in WebAssembly. The same holds good for C and C++ as well. There is a framework called mscriptin, and also the same with Zig. In fact, I did a live stream with the Zig programmer last week where he was talking about the support for Zig and WebAssembly, and it uses LLVM under the hood, right? So you write code in C and C++. There are these frameworks, and it outputs a WebAssembly module, and you can go for it. Now, interpreted languages are a little trickier, right? Because in the case of something like Python, you have an interpreter in the middle. So how do you actually change that Python code to WebAssembly and make the interpreter understand WebAssembly? Because the interpreter is meant to understand Python. Well, actually, there was a very smart way that people came up with an idea for this. So you typically write any program, compile it to a WebAssembly module, run it on a WebAssembly runtime. So in the case of interpretive languages, what people did was they took the interpreter and they converted that to WebAssembly. Right? So this was a task that is undertaken by language teams and is done pretty much by hand. So the Python interpreter is converted to WebAssembly. And then when you write Python source code, that is provided as a Python input as well. So what happens is just at the time of execution, there is a just-in-time snapshot that's taken of both the WebAssembly interpreter and the Python source code that you've written, and that creates a WebAssembly module which runs on a WebAssembly runtime. Yeah, so it's a very smart way of doing this. The sort of drawback is if there is a new library in Python, then that has to sort of be rewritten or written in WASM for it to be supported. Right? So all the popular ones like NumPy, etc., are supported, but say you have some internal or a very rare or not common library, there might not be support for that in WebAssembly. And of course, with the virtual machine languages, it's kind of tricky because the virtual machines themselves do things like garbage collection, memory management, all sorts of different optimizations. So I would say languages such as Java and .NET still are yet to have like full production support when it comes to WebAssembly. But I know that the language teams, for instance, in .NET are working on, adding some sort of support. So there's a good matrix up available of the different languages. So these are RedMonk's list of top 20 programming languages worldwide. And you can see the support for the core browser, WASI, which is to run on the server side, and so on. Right? Of course, languages such as CSS and Shell don't count. I mean, they are meant for different things. But you can see with JavaScript, Python, C, C++, even Swift, there is pretty good support to write in WebAssembly. Cool. So I just spoke to you about the ability to write in different languages and convert to WebAssembly. Let's actually talk about security. And the fact that every WebAssembly module is security sandboxed by default. And this becomes very powerful when you talk about server-side. Now, again, we're talking about Bangalore's history as well. And if you've been to the airport, you've probably come across the name of the airport, which is Kempegowda International Airport, right? So talking about security, Kempegowda is regarded as the founder of modern-day Bangalore. So essentially, in the 1500s, he came by this part of land and he fortified the city. So he created a fort in the south of Bangalore. It's still around. It's called Bangalore Fort, just on the outskirts. And this is an old British map. And he set up 4 towers to demarcate the border of Bangalore. In fact, this tower is about a 20-minute walk straight up the road. So just go up to Mekri Circle. Right at the circle is this tower. And there are 3 other towers in Bangalore. And back then, they demarcated the actual border of the city of Bangalore. Of course, Bangalore has expanded far more than that. But you will come across the name Kempegowda in the airport. There are statues of him. There are streets named after him. Very famous person and regarded as the founder of modern-day Bangalore. So just as Bangalore had these towers sort of demarcating it for security, WebAssembly modules, like I mentioned, are also security sandboxed by default. So this is what I showed you earlier, right? You had a function to add, a function that calls the other function. It runs in a host runtime. Now here's the thing, if it's security sandboxed by default, can it really do much? Like, how do you access it? How do you access files? What's the deal with that? Right? And say I'm a developer and I want to access this function. It's not allowed by default. So what do? The good thing is it was designed ground up for you to export functionality. Right? So I have this function to add numbers. I also have the ability to export that WebAssembly function. Right? So I can export what it does so that other people can actually use it. The cool thing is, as a user, I can access that exported function and do something with it. The cool thing now with this WebAssembly module is you, as a function, can also import functionality, right? So if you go back to our function right here, all it does is just add a number. But say I also want to print it out, So I can get someone to write a function to print a number. So in this case, what we're doing here is we're writing import console.log, and we're printing the number that's sent to it, and we have called a call print, right? So we have this function. Our old guest WASM module can also import this particular ability to print a number, right? So the developer has supplied a function, which is the ability to print a number. The guest WASM module, it imports that particular function and runs it and prints the number out. Right? So with this method of importing and exporting, you're still keeping the security sandbox, but you're having this ability to communicate within modules as well. And just to make things better, when we're writing programs, we need to store some data, right? And we have this concept of memory. WebAssembly has this concept of a shared linear memory. Now, again, quite a mouthful. So we know what memory is. We want to store some data. Linear memory is, in WebAssembly, you get any module gets a contiguous block of data as memory. Now, if you've studied heap memory and things like that, sometimes in different programming paradigms, you actually get different addresses spread out in a heap storage, right? But in WebAssembly, you get a contiguous block of data for your memory. And the reason it's shared is that it is shared within the host runtime. Right? Remember the hotel analogy? So within that host runtime, it's actually shared between the host and the guest. So in this example, we are importing console.log. We are importing some system memory, and we want to print out hello world. So we actually call this function hello world, and we define the first byte, which is 0, and hello world in its entirety is 14 characters. So we say go to the next 14 characters and then just export that function, right? And this is what it looks visually. So we've added more things. As you can see, the user invokes the export hello world function and supplies a way to print this out. Our guest WASM module is initializing this and printing it out. But the cool thing is both have access to the shared linear memory, right? The WASM module is accessing the shared linear memory and getting the hello world from there. And the shared linear memory reads, and that's how it's able to import and use the print function, right? So this concept of a shared linear memory is super important. Also important to remember again that this is denied by default, right? In any WASM module, if there's a bad actor, for instance, right? Say this WASM module is a bad actor. The interesting thing is none of the other WASM modules are affected, and it can't have access to the underlying files, right? So that security is of paramount importance, because if this was a bad actor, it would have access to the shared linear memory, but nothing underlying in the system itself. So when you're running it on a server, it becomes quite secure. Okay, so I spoke about security, and I drew parallels to Mr. Kempe Gowda. We're now going to talk about portability, the ability for WebAssembly to run cross-platform and cross-architecture. In our history of Bangalore, we're going to go for about 400 years in the future into this building. Has anyone seen this building? Again, not too far from here. So this building was built in 1956, and it's called the Vidhan Sauda, right? And this is the state or the seat of legislature right off of MG Road, which is pretty much the center of the city. So India got independence in 1947, and the erstwhile capital of Karnataka was Mysore, but then it was moved to Bangalore after independence. So the chief minister of Karnataka then was Kengal Hanumantaya. If anyone's been to KH Road, that's named after him. And he said, hey, look, all of our newer buildings in the last 100 years are all buildings built by the British Raj. We need something regal, we need something grand to sort of show our own culture, right? So he commissioned this particular building called the Vidhan Sauda. And I think it's a very beautiful building because it combines different elements of different styles of architecture. Officially, it's called Neo-Dravidian, or a new form of Dravidian architecture. Dravidian architecture is architecture in the south of India. So if you've gone to temples in the south of India, you will see a very particular style of architecture called Dravidian. And the cool thing is Vidhan Sauda takes elements of that, but it also takes elements of this other school of architecture called Indo-Saracenic architecture, which is a combination of some European styles with Mughal influences. So if you see the things like the domes, they're very influenced by Mughal architecture, but you have things like the columns, which are very, from the European styles of architecture. And I think the cool thing is in that area itself, you will see multiple buildings with very different styles of architecture. There's a brutalist building up the road called the M. Vishveshwaraya Tower. Right opposite this is the High Court, which has Doric columns like you would see in Greece. Right? So in this one street, you have all of these different types of architecture. And just like that one street in Bangalore and the Vidhan Sauda in Bangalore, WebAssembly does support multiple architectures and platforms. Right? So essentially, any WASM module can run on a WebAssembly runtime. And there are different types of runtimes. On the browser side, you have the browsers itself. So SpiderMonkey, Chromium, you can run it there. If you want to run it on a server side, the most popular one and the industry standard is WASM time. It's run by this thing called the Bytecode Alliance, which is kind of like W3C or CNCF. It's a consortium. There's also WASM 3 and a few other runtimes. A WebAssembly module can theoretically run on, say, WASM time. And WASM time can run on any platform and any architecture, right? So like I said, any OS, Windows, Mac, Linux, Intel, ARM, etc. So this makes it extremely cross-functional, cross-portable, and really takes that idea of write once and run this anywhere. But the question is, how does a host runtime execute my WASM module, right? What's actually happening? So you have your WASM module here, and there are 3 semantic phases for that WASM module to actually be executed, right? The first one is called the decoding step, where essentially this is kind of like a bookkeeping step. It is just it checks the internal representation of your WASM module, and if it's what it says it is. And then there is a validation step where everything about the code that you've written in that WASM module is double checked. So it checks for if your function's too long, if the functions that you call are actually there. There are some other security steps. So this is a validation step right there. Once that's done, your module is actually instantiated and it goes into the execution phase where your module then is actually executed. So again, the instantiation itself is a bookkeeping step, and then the invocation invokes the specific function that is in your WASM module, right? So it's 3 steps where you decode, validate, and then execute this on the runtime. And the runtimes are written for you to be able to run it on cross-platform and cross-architecture. I told you I will show you an example and compare it with how Java works, right? So for those of you who are familiar with Java, you write a Java program, you compile it to Java bytecode, that executes in a JVM, which can run anywhere. So ARM, x86, whatever. WebAssembly has taken that a step forward where you can write code in any language, which compiles to WebAssembly bytecode, which runs on a WASM runtime, which can run anywhere. Yeah. So in terms of the concept, it's very similar, but in terms of how it's executed and how it's built, there are a lot of differences. And the cool thing is WebAssembly is not proprietary, unlike, say, things about Java, right? So WebAssembly it's a binary format, so no one really owns it. All right. So I spoke about portability and the ability to put it in different architectures. The last feature that makes WASM great is the performance feature, right? And how you can actually get near native execution speed. So we're going to fast forward from the 1950s to the current day. And I think it's safe to say that Bangalore is the sort of Silicon Valley of India and the IT hub of India, right? There's so much action happening here in the IT space, from services to products to startups and so on. It's very important to remember where it all started. And in the early 80s, there were companies like Infosys and Wipro that started homegrown services companies here that started the IT revolution. But the first ever multinational company to come here was in 1985. And the photo that you see here is an actual photo of a satellite being loaded on a bullock cart for this company to speak to their US counterparts. Does anyone know which company this is? It's a famous piece of trivia. No? So this is Texas Instruments, right? So Texas Instruments was the first MNC, or multinational company, to set up shop here in Bangalore. They actually got a satellite on a bullock cart, set it up, again, not too far from here, in Sohan Towers, very close to Cunningham Road, just so that they can speak to their colleagues in the US and work from Bangalore. And we've gone from that to the insanely good IT scene that is here in Bangalore. And I think it's safe to say that it is fast moving, it is dynamic. And again, I want to run that near native performance and speed of WebAssembly as an analogy. So how WebAssembly actually does this is different ways. And the performance, you can see performance, I'll show you a benchmark as well, with things like JavaScript in the browser, where WebAssembly is much faster and much more performant. How it works in terms of running some program is it runs on something called a stack machine. And for those of you who have studied CS back in the day, you might remember some of this. So we're going back to a good old WebAssembly module, right? An addition function plus one function. So a stack machine, we are sending addition of 4, 3, right? Which is the addition of two numbers. So there is a stack. So when we say parameter LHS first, which left-hand side, which is 4, that is pushed into the stack. Then we say parameter right-hand side, which in this case is 3, that is pushed into the stack. And then the two numbers are actually added. So how WebAssembly works under the hood is these two numbers are thrown out of the stack, and the result is pushed back into the stack. So any computation works on this stack-based virtual machine. And this stack-based virtual machine basically enables performance to be much faster than, because different programming languages don't necessarily do it this way. Because there are just-in-time compilers that transpile this and then do optimizations to the hardware that it will be pushed to, right? And all of those optimizations help in performance. In fact, maybe I'll just show you a quick demo as well. It's just a benchmark I found online, which is a performance test, right? So this is code written in JavaScript and WebAssembly. And you can see the frame rate right now, it's in JavaScript. I can do something like this. I can add noise as well. Yeah, and we're getting about 66 frames per second. But when we switch to WebAssembly, we see that number shoot up, right? And that is the performance difference here. Clearly, like, significant performance between WebAssembly and JavaScript. Cool. So that was the fourth reason why WebAssembly, really shines and is poised to be a big deal. Now, I mentioned that this was built for the web, right? And with these features in mind. But sometime in 2018-19, people were like, hey, wait a minute. This could actually make sense on the server side as well. We want something that is secure, that is fast, that you can write in different languages. But for something to run on a server, you need things like access to files, to system clocks, to networking, sockets, and so on. So in 2019, there was a new spec that was written called WASM, or WebAssembly Systems Interface, right? It gave WebAssembly an interface to talk to a system. And the TLDR is it allowed you to run WASM outside of the browser. The cool thing was it gave you access to all your OS features like files, file systems, clocks, and so on. And you didn't need to use a browser or JavaScript. So now you can run it on a server side. And it extended that security sandbox that I spoke about. So you can still do that security sandbox with an input-output for files. And if you don't believe me, I'm just a random guy. There's a famous tweet by this guy named Solomon Hykes. You may know him as the founder of Docker. He's the guy who created Docker. He actually tweeted out in 2019 saying if WASM existed in 2008, we wouldn't have needed to create Docker, right? Because really, that is how powerful this is going to be on the side of cloud computing or on the server side. And I'll talk to you a little bit about why. So I thought I'll show some code as well on creating a WebAssembly app. I'm going to show it with this open source framework called Spin. Right? Spin is a developer tool for building WebAssembly microservices and apps. It's completely open source, close to 5,000 stars on GitHub. Feel free to contribute, do it. It's fully open source. We at Fermion, we maintain this Spin repository, but again, it's completely open source. And yeah, I'm just going to show you a simple hello world example. And I'll also show you how the security and some of those aspects work. Right? It's going to be tricky because I have to look at that screen and try and type, but I'll see if I can make it work. All right, so I have my terminal. I've installed my CLI already, and I hope you can see my screen as well. You can see your screen? Yeah, all good. So I have the CLI installed. I'm just going to do something like spin new. Now, these are templates in Spin. I mentioned the ability to write polyglot, right? You can see all the different languages supported right now. You have Zig, TypeScript, Swift, Rust, JS, whatever. I'll pick Rust because I hear all the cool kids are doing Rust. Let's pick Rust, and I'll just say GIDS, right? So we are actually building a server-side WebAssembly app. And it is how it works is it gets an event, and it runs piece of code, and that's it. So for something to get an event, you need like a URL, or you need a path we can set the default path here in the next step as, anytime this is pinged. But you can also do like /checkout or slash something. All right, so this is the default. We just set that, and I will do this, and I will open it in my code editor, which you will see here. Okay, so two things to remember in a WebAssembly program. One, there's something called an application manifest, which it's like the nucleus of your program, right? It sort of tells you all the important information. As you can see here, this is where it will output the .wasm file that I spoke about later. This is some metadata, and these are the different triggers. Right now it's a default trigger, but I can also say /checkout, /image, and have different routes. The very cool thing is, in this same Rust program, I can add Python, I can add TypeScript also, right? So like I said, that's the ability to write polyglot programming. I'll keep it simple in this demo and just do Rust. This is simple hello world, so I'm just going to go to the source file. The code here is, again, pretty straightforward, right? I will just say gids and save that. There's a request coming in. You're passing that request, and you're sending a response, right? Very simple request-response model. If you've heard of things like AWS Lambda or Azure Functions, it works in a very similar way, right? It's event-driven. So you get an event with a request, you do some things, and you send a response back. Yeah? Here we're not doing too much. We're just sending a response called hello gids. Going back to my terminal, and I'm going to build this. Let's say it's been built. What it does is it looks at that application manifest. It fetches some crates. The first time you do it is a little slower than the rest because it has to fetch the crates, sort of like doing an npm install on TypeScript, for instance. And yeah, once all the crates are fetched, I can actually have this app up and running on a local server on my machine. So as soon as this is done, and it's done, I will just do a spin up. Right, so this creates a local version running right here on my system for me to test. So it's created it at home. I can copy that. I'll just do a curl. Oops. Right? And I see the hello gids response. Right? So in hardly 3 commands, I was able to create like a local WebAssembly app written in Rust running right here. I did say with WebAssembly, you can write code in multiple languages. So if I can find my mouse pointer, yeah, there it is. I wrote a simple program in TypeScript, right? So this just makes an API call. You don't need to know TypeScript for this, but I'm just calling a random API which has a JSON, and I just call that API. I just get the response back, and I print it out, right? It gives us a physics fact. You don't need to know about TypeScript or anything else, but essentially it's just a JSON API. So I'm going back to my terminal. Let me do this. Yeah, so I will do spin build. So this will build the program right now. And then I want to get the local thing up and running, right? And we should see, oh, I should close this one. Sorry about that. I close this. Yeah, so we should see this now. And you should see some strange error, right? There's an error that says destination not allowed. Now, remember I told you WebAssembly is security sandbox by default. So anything including access to files and APIs have to be explicitly set. And that's the security aspect that I wanted to highlight. So right here in my spin.toml, I have to explicitly allow access to outbound hosts, right? Or if I want something else to access this, I need to allow inbound hosts. If I want this to access a file on the system, I need to allow that, right? It has to explicitly allow because it's denied by default. So now that I've given access to outbound hosts, I can save this, go back to my terminal, do a spin build, and then a spin up. And hopefully now, again, I should just close this. Right? So now hopefully our curl should work, and hopefully our internet is good enough. Ooh, I'm in the wrong folder. But, oops, I think I built the wrong file. I can open it in a browser as well. Yeah, oh, I don't know why this is happening, but we'll get to that in a bit. Let me just build that. Oh, I'm in the wrong folder here. Sorry about that, folks. HTTP outbound. I'm just building it again. Ugh. Yeah, I built it. And I'm going to make the curl call again. Right, so it's making a call to the HTTP API that I specified, and it's given me a physics fact, right? So what I wanted to highlight was the security component, where even a call to a API has to be explicitly given. All right, so that was the live demo. So hopefully so far, you have a good idea about how WebAssembly works, why it makes sense. Now, I'm here to tell you that this will actually change cloud computing. Now, I worked in the cloud computing space for a while. My previous role was at Amazon and Amazon Web Services for the past 6 years. Had a close look at how the evolution of cloud computing is going, right? And we're moving from this whole going from on-premise to going to the cloud with virtual machines with things like EC2, where you had to take care of the entire OS. It was much slower, and it didn't have the greatest developer experience, but it gave you the cloud, right? This was the first thing. We went from that to containers, right? And I think most big enterprises nowadays are on Kubernetes, Docker, etc., where you take care of your application and your deployments. It's still not the fastest, but it's much faster than a virtual machine, but it enables things like scaling with a reasonably good developer experience. We've gone from that to the concept of functions and serverless, right? Serverless things like AWS Lambda, Azure Functions, Google Functions, where everything is event-driven, everything takes just milliseconds to start, and you have very simple and good developer experiences, right? So WebAssembly is poised to make a difference in the containers and function space. One is, anyone here use containers at work? Few of y'all, all right. So the one big problem with containers right now is the fact that when we're provisioning a container, we do that for the maximum usage. And very often there's a difference between your peak usage and your average usage. If you can get that as close to each other, you're doing a good job. But typically that's not the case. And just in a report on Next Platform about a month ago, they saw that the average CPU use is about 13%, right? So your containers are taking these computing resources and are doing nothing with it, and you're paying for it. And unfortunately, that is the nature of how the container ecosystem works right now. Even in large clusters with 1,000 CPUs or more, that CPU utilization was only about 17%. And here's the thing. It sounds counterintuitive, but the more you use a system or the more you utilize a system, the more value you're actually getting out of it. Because idling systems actually take up resources. They take up memory, they take up power, and this cost is borne by you as a developer. The thing is, with WebAssembly, you can have very lightweight apps run in your Kubernetes cluster, which takes some of these problems. So for instance, a Hello World Spin WebAssembly application written in Rust is only a 284 kilobyte artifact, right? So if you create like an OCI artifact, that's just 284 KB. If you take any web like Kubernetes Hello World app, that's a lot bigger because of the underlying Kubernetes infrastructure, right? The files and so on. But in a WebAssembly app, that's a lot smaller. I can maybe even show you that app that I was talking about. So this is the HTTP outbound app that we wrote, right? If you go to the target, you will, cd target. Yeah, so that is the WASM file that's actually created. We can try reading it, but I don't think we'll understand really what's written here. But you can actually see the file size, right? It's about 2.3 MB. It's a really small WebAssembly file, which actually sends an HTTP call. The same thing written in Python Flask, for instance, would be maybe about 20 MB. And so that's, at scale, makes a big difference. The next reason is the startup times. Now, because WebAssembly is designed to be performant, it can start up and scale back down to 0 instantly. Right? I'll talk about cold start times in a bit. I mentioned and showed you how they are security sandboxed. So in a Kubernetes cluster, typically it's not. But when you're writing in WebAssembly, they're sandboxed by default. They don't have access to the underlying system resources. And they're portable across architectures as well. Right? At the KubeCon keynote, Zeiss actually showed a demo where they did this. They swapped out the underlying architecture from x86 to ARM, and the thing still worked because they were using WebAssembly, right? Because it doesn't matter, it's cross-platform and cross-architecture. At KubeCon, there was this new CNCF project, which is open source, that was released called SpinCube. Again, fully open source, so feel free to contribute to it. It was built in collaboration with some of these companies that you see here, and it's a way to deploy WebAssembly apps on your Kubernetes. Very new, about a month old, so check it out. Good way to deploy very dense number of apps in one Kubernetes cluster. So the first way it would change cloud computing was fix containers. The second way is fix serverless. Just to context set, serverless is a way to program or way to do cloud where you or me as a dev, we don't think about server functions. I don't think about server maintenance. I don't think about server daemons. Now, if you use Lambda, Azure Functions, I'm a big fan. I think they're great, but there are a few problems with serverless right now. One is the developer experience is a little complicated. There is no great local testing experience, as you saw now. Two, and very importantly, there is vendor lock-in. If you're using Lambda, your entire serverless stack is AWS and Lambda. If you're using Azure Functions, you're locked into Azure Functions. The third is cost, because this ends up being a little expensive. And serverless has this problem of a cold start time. Essentially, an event happens, you send something to your serverless function, there is a finite amount of time for that function to start and then execute, right? And that is called a cold start time. And this is because of how it works, right? So basically, there is some unused capacity on EC2, send a function, it starts in KVM, and then it executes, sends a response back. To reduce that, companies do things like keeping your function warm, right? Where they send periodic pings to keep your function warm, but that cost is borne by you as a dev. But with WebAssembly, because it's so performant, you can bring those cold start times down by about, from 250 to 500 milliseconds to about 50 milliseconds. And again, this is because of how WebAssembly actually is. So you end up saving a bunch of money, you end up having much faster serverless applications as well. So I've spoken a lot today about WebAssembly, front end, back end, Bangalore as well. I want to sort of end with what the future of WebAssembly on the server side looks like, right? And that future is something called the component model. So right now, when we're writing code, we write like a code base, which is all in the same programming language, Python, Java, whatever. And because of this, there's a lot of code that is actually reused throughout, right? So say I'm writing a code, but I'm writing code in Python, right? And I need a YAML parser. Python doesn't have a good YAML parser, right? So then I have to create my own YAML parser in Python. That's just a waste of time. So the component model enables to change all of that. So in the near future, and even now, in fact, your JavaScript app can talk to a Rust YAML parser and can also talk to a Python date formatter, all in the same program. Because each of these will convert to WebAssembly, which can all work together, right? So this is the future of WebAssembly, which is the component model. It's very exciting. It's live right now. You can try it out yourself. The developer experience around this is in a state of evolution, but I think it's exciting, right? For the first time, we can get this polyglot programming within one application. And this has so much potential to change how we think about code and programming. For instance, your event-driven microservices architecture can be in different languages, across different clouds, across on-prem, across your Raspberry Pi as well, without the need to be locked into a language and a provider. I'll show you how this would look in reality. So say you have a WASM module, and we already know that it's portable, it's small, it's fast, open standard, etc. You can write code in any language, right? So say you create a component oh, sorry. You create a component A in WebAssembly, in any language, that can export a certain function. And this component B is like, hey, I need to use that function, and I don't want to write code again for that. So component B can import that functionality from component A. And these two can be in different programming languages. So I can write something in Rust, which exports a function, and I can write something in Go, which imports that same function, right? And what you're doing is you're creating a new component. So this is the idea behind how the component model works. And it's cool because it's completely language interoperable, it's composable, and it retains all of the performance benefits, the security benefits of WebAssembly, right? So do check it out. This is where the future of WebAssembly and server-side WebAssembly is going. All right, so I'll try and recap everything I spoke about because, just in case your attention wavered at some point of time. So I spoke about how WebAssembly is a there's a bytecode format that's gaining popularity. I'm going to restart PowerPoint, but that might take a couple of seconds. Yeah, but I spoke about how WebAssembly is a bytecode format, right? It's not owned by anyone, or it's not a proprietary technology. It's a format, and it's gaining a lot of popularity right now. There we go. 2, we spoke about the benefits of WebAssembly, right? What makes WASM awesome? Spoke about polyglot, writing code in multiple languages, security sandbox by default, portability, cross-platform, cross-architecture, and performance, and near-native execution speeds. This new spec called WASI enabled us to run WebAssembly on the server side, where we think it'll make a big difference. I showed you a demo of Spin, an open source SDK. I spoke about how WASM will change cloud computing and is changing cloud computing, and also a short history of Bangalore. Very quickly, this is just some attribution for the images I used today. For next steps, some things that you all can take down, and here's where, if you want to take a photo, some links might be useful. If you're interested in the nitty-gritty of how WebAssembly works, Mozilla's MDN docs are great, excellent resource where they explain some of the things I spoke about. If you want to write code, check out Spin. It's open source, github.com/fermion/spin. If you want to read a children's book about WebAssembly, yes, it is a children's book with illustrations and funny characters. There's Fippy's Field Guide to WASM. Or if you want to look at the future of WebAssembly, check out the component model, right? And how the component model works and how it will be executed, and you can also play around with. Anyway, this has been great. I hope you learned something new. I had a good time. Feel free to connect with me on LinkedIn or talk to me here as well. We have 5 more questions, so if anyone has any questions, you can ask now. But also, thank you for listening in. Thanks.